So I have access to all the College Board questions they've ever asked and all the questions that they propose and they don't ask. And I'm not allowed to show you a lot of that. But of the stuff I can show you, there's a few really discrete patterns. So I just want to make you familiar with some population curves. Hint, likely to show up on our unit exams. And of course, promise, gonna show up on your AP test in May. 1 or 2 points. It's not going to be huge, but there's a few things I'd like to point out. So I want to just show you like a few slides that have these images. First of all, exponential growth is when you're growing by a percentage at every step in time. So as your value gets bigger, the same percentage of a bigger number is more growth. And so the curve keeps getting steeper and steeper, and this continues until it appears totally steep. Called a J curve. That's a term you should know, and that's exponential growth, versus logistic growth, which is where that carrying capacity kind of starts to that population growth kind of starts to slow down when, environmental limits start to lower the success of new individuals, where you kind of start to hit a roof of some sort. That's called carrying capacity, which is often abbreviated as K, and everybody can spell. I once heard the reason why it's K, and I have forgotten. It's been too many years. It's not a misspelling. Now, there's this thing that happens as you go through time, and you should probably know what the breakdown is. So if you don't mind, I want to read you what this says. At any time where you have more birth than death, population will grow. Obvious. And if resources are abundant, there are no limits. So you tend to have fastest growth before you start having limits. Now, limits means somebody couldn't get a house, so death rates start to come up. Or somebody couldn't find enough turkeys, and death rates start to come up. In other words, same number of births, but more of them dying, that growth is going to slow down. That asymptotal behavior is called logistic growth, where you start to level off because of limits. People call that density-dependent equilibrium, where the number of individuals tells you where you're going to level off. You'll eventually reach a maximum population depending on how many are there. We'll come back to that density-dependent term in the reading packet. You may want to write that on the side, density-dependent, in your notes. And remember that carrying capacity is symbolized as K. Now, it's possible that you can overshoot, like have too many offspring, and then the resources run out. So rabbits are famous for doing this. Rabbit populations grow so fast that all of a sudden you've got 48 billion bunnies on the football field, and they run out of grass at the same time, and then there's this population die-off. Bunnies are famous because of the rapid population growth. They'll be like, oh, there's plenty of grass, and they all eat, and there's plenty of grass, and they all eat, and all of a sudden there's like 16 adults for every one last week, and now there's not enough grass. So stable, growing, overshoot. When you go over the carrying capacity, that's called an overshoot. And then, resources start to run out, so population starts to drop. This is called a dieback. And eventually that equilibrium state, that leveling off. So here's something that I've seen repeatedly. A is how many they could have. Biotic potential is like what would happen if there weren't limits. Like, a man can make a child every 45 minutes if you try hard enough or something. A woman can make a child every 9.5 months or something. That's the biotic potential. B in this case is just a random distractor, but it does actually come from a data set, that rabbit population thing, where rabbits die off and there's not a lot of breeders and the population starts to come back and it overshoots and then you die off and then you overshoot. So B is usually a distractor, but that does come from real ecology. I have a textbook from like 1996 that had that curve in it. C is the logistic growth curve, the one I told you about earlier. See, logistic growth. C is that one where, you know, limits are reached. Now, D might be a distractor. You should notice that that's a straight line. Every unit of time is the same growth. So for every one of these, it goes the same amount of that. Every one of these goes the same amount of that. So that's linear growth. That has no place at all in a discussion of populations. There's no biological population that grows linearly, so that's probably a distractor. And remember that that limit, which is capping the growth of curve C, that's called the carrying capacity, the total amount of individuals that can be supported by an environment. Now, there's stuff that they'll have in the textbook about growing fast, growing slow, dying back, whatever, and that just depends on the curve, right? So like slow growth, rapid growth, slow, it's like how steep the curve is. If you didn't know that, you should write that down. Growing fast is a steep, growing slow is a shallow curve. You can like grow but at a smaller rate over time, or you can have negative growth, which is a shrinking population. I've seen all these words and all these graphs used by the College Board. So if they weren't familiar to you, you probably want to go back and fix your notes. But if you understood all of that lingo, maybe this was not relevant for you. All right, thank you for watching.